Any questions?
For the one, everybody's turned in their stuff, right?
Yes.
We weren't supposed to take into account the negative on the distance in the first one, right? No.
I took it, I took a negative distance.
It's electric potential. See, there I had the decency to define it. Yeah, the negative would be taken into account.
You're talking about the negative charge?
Yeah.
Oh, yeah, no,
Oh.
the R, the KQ over R, would there be a negative?
Oh, not the way that I do it, no.
So if I cut the distance in half to what, like, right, and then just do the same 0 point, whatever, 445?
Yes.
Yeah, okay, and then just take the charge negative into account.
Oh.
The second one, we subtract it from the first one, and that's it.
Yes.
It would be
Yeah.
negative, negative, cancel, subtract, so it would add.
Well, add a
What if you add
negative.
them? Because
Well, you had them, but it ends up being subtracted because of the
the
charge.
electron go to the positive charge for a higher voltage.
Did you get like to the -5?
One electric potential's positive, the other
Yeah.
electric potential's negative.
You got a really big
Add them.
number.
Yeah.
I'm in positive 5 or 6.
For what?
Number one. Never mind.
Well, yeah, I mean, if you did the,
Yeah.
scientific notation for
That's
it,
fine.
yeah, I just got a big number in general.
Any other questions? We last left off, we did resistors in series and in parallel. Or do we end with defining resistivity?
Oh, I'm good.
So, okay. So you have this solid metal sphere at the center of the hollowness. And you're looking for the total charge on the exterior of the inner.
Right.
So this function gives us the electric field just outside of this sphere.
Okay.
So, but when I'm looking to find the charge of this sphere, you know, from this, this outside point, do I take into the account this hollow?
Because of spherical symmetry, you only worry about what's inside.
Even the inside layer of the hollow sphere, that doesn't have any effect on it?
Yeah, you were only looking for the things that are within 7 centimeters.
Me and Mike, what?
Right. We derived Ohm's law. That's the last thing we did. I'm guessing, or is there more?
Yeah, no, I think that's basically it.
We derived Ohm's law and then we just wrote out all the units,
And then what?
like wrote out all the units.
Units, okay.
Like
All right.
the Henrys and, they're
And Bose.
Or is it Maho? All right, so we have the basics down, and so it's now time to start doing some circuit analysis. So Kirchhoff has 2 rules. There's the current rule, or also known as the junction rule. And then there's, what?
Did we not talk about that?
Sorry?
I don't remember the junction rule.
Yeah, because
Yep. This is the next, I assume that we covered Ohm's law, so we're going to the next step.
I could have sworn we covered this stuff.
Did we? Okay.
Hold on. Maybe I'm mistaken, I'm just.
Well, if you can't remember, maybe we need to go
No,
over
we
it
did,
again
yeah,
anyway.
we did it before Ohm's law. We did a voltage loop. It's where the end resistor and potential changes, and then we have the current junction rule, where at any point current is the current
Okay.
in is current out.
All right, so this is a rehash. So current rule is that at any junction, and the junction is where current can split, total current in equals total current out. voltage rule is that the sum of the voltages around any closed loop is equal to 0. So we're going to use that concept. If I take a battery, put a resistor into it, so let's make this a 12-volt battery and a 3-ohm resistor. As I go around the loop, I know that the potential difference between this spot and itself is 0. The potential difference, I guess we can write that as the potential difference between point A and itself is 0. It better be. So what I'm going to do is I'm just going to go around my loop here. So I go across my battery here. Doesn't matter which way you go. I'm going to go this way. It's also the direction of current. So current's going to be flowing this way, or sorry, my loop's going to be flowing this way, up, over, around, and when I get back to there, that should be at 0. For my battery, which is the positive, which is the negative side?
Positive, big one.
Okay. So as on my loop here, I go from the negative to the positive, which is an increase in potential. So I gain 12 volts. Cruising along here, going across my battery. Now, the idea when they defined current, when I guess Benjamin Franklin was using the water analogy, and he figured current flows downhill, it flows to a lower potential. So as I'm going across in the direction of my current flow, then I'm going from in the direction of current flow, I'm going to a lower potential, and so I'm going to lose potential going across my resistor. So minus the change in potential across the resistor, and then I should be back at 0. From Ohm's law, I know that that has got to be equal to the current times the resistance. And so therefore, we end up with the current flowing across it is going to be 12 over 3. So 12 volts over 3 ohms.
There's a
Fancy
complex
math.
math behind the
Yeah.
integration and all.
If you need help with your calculator, figuring that out, just let me know.
I think it's 4.
Let's just go with it in case, if somebody can correct us if we're wrong. And units? Not a unit.
Volts over ohms.
You could get away with volts per ohm. There is a one-word
Amps.
amps, or amperes. Now I'm going to write this slightly differently. My battery there, we have, I say it's a 12-volt battery. In reality, a 12-volt battery is not really 12 volts. Even if I hooked up a voltmeter to it and it said 12 volts, that doesn't necessarily mean I've really 12 volts, because potentially I'm going to have some resistance within the battery itself. So once I start running current, there's going to be a little bit of a loss there. So some textbooks will do a battery and they'll throw a little resistor in there and they'll put little dotted lines around that. And they would do something like that, so you would have to take that into account. Now this resistance is tiny, I'm not worrying about it, and so I tend not to do that, but technically there's something there. So the practical voltage and the ideal voltage are slightly different. Now the ideal voltage has another name, of course. It is the EMF, symbolized by capital epsilon. Or in OpenOffice and LibreOffice, it would be the variation of epsilon.
Is what am I thinking of? Free space, permittivity of free space, is that a lowercase epsilon? Or no?
Yeah, I tend to draw a smaller one for that. I think that's lowercase. Yeah, that's, again, repeating letters. All right, now, for what does the EMF stand?
Electromagnetic field.
No,
Good guess.
Yeah.
not quite there yet. Usually somebody comes up with the old answer.
What was the question?
What does EMF stand for?
Is E electrostatic?
No, E is just electric.
Magnetic fluctuation.
Magnetism is non-volatile. Right. The reason I ask it is that if you ask most people, or those who have an answer,
Electric median force?
What is
it was originally electromotive force. I guess electromotive, not electromotive. The electromotive force. Because when they first were dealing with this, they thought it actually was a force. It turns out it's not a force, it's a voltage. So officially, EMF now stands for EMF. Historically, it stood for electromotive force, and so some people will give that as the answer, but it actually does not stand for that anymore because it's not a force we're talking about. So this 12 volts here, I'm just going to assume is the EMF. And so I would really write this as the EMF minus IR equals 0, just doing substitution at that point. And so I would be the EMF over R. This is just for a simple one resistor circuit, and obviously on Thursday, we will get into what happens if there's more than one resistor. And that would be the cliffhanger.
Then we're gonna have stuff that's gonna be so complex and big.
Or
This resistor is small. And you're gonna have an inductor, and you're gonna have everything.
Yeah, so
Are we meeting in here Friday or are we meeting in
in the, well, oh, I'm a week off there. God, I was thinking the test was next week.
We can make it next week if you want.
Next week would be amazing.
I mean, the more we push it off, the more new material we're gonna cover before you get to it.
And then
I
assume
will
we're gonna
say-
have the other tests like close to each other.
Yeah.
I will say from experience, being halfway through the second unit and taking the first test.
And I probably mentioned it before, I have finished the material for the second test before the class has taken the first test before. I don't think they appreciated that.
How long are the tests?
I looked at the test, I guess, for that.
Okay, no problem. They should be like the same format. They should be
Pretty much the same format.
Different questions.
Potentially.
Okay.
I take an old test.
It was like
I the
7
whole
of them,
thing in
so.
yellow.
Well, one of the tests that you had on there was like all multiple choice, I think, or, no, wait, maybe they're
It was
just different
parts.
parts, they're different parts, okay.
Yeah, there were some early ones where I had more multiple choice than I do now. All right, would you rather take it in here or take it up there?
And you're.
All right. We'll assume it's gonna be in here then on Friday, unless I find out otherwise. I don't know if
Maybe the
classes-
weird,
Probably not.
Race theory or whatever that they do before this class. When you-
Oh.
Maybe their class is holding session on Friday.
That's possible. But I think the only people who really do Friday classes are science people. That's right, we accept